So last time I showed you how to use the theory of differentiation, the theory we have developed so far for functions of two variables in order to find first local extreme values and then global extreme values. So maybe one more easy example which is already a good motivation also for what we wanna discuss today. So the last method we have discussed is a method which is similar to what we called last semester the closed interval method. So we have given a function on a domain which is assumed to be closed and bounded. And because there is an analog of the extreme value theorem, namely there is a extreme value theorem for functions of two variables, which tells us that for such a function which is continuous on a closed and bounded domain, such a function must attain absolute maximum and absolute minimum. Now, this result gives us is the basis of a method which is similar to the method which we call the closed interval method last semester, and which works as follows. So you have given a function on a bounded and closed domain. What you do is you find the critical numbers inside the domain, and then you compute the function value at the critical numbers, and then you check the boundary. And so more or less for the boundary you have to consider all function values. This consists, of course, the boundary was more easy for a function of one variable on a closed interval because you have just to check 2 points. But here, for a function of two variables, the boundary can be much more complicated, and finding the largest value and smallest value on the boundary is not necessarily very easy. But if we can do it, then what we do is we check the function value on at all the critical points inside the domain. We check the boundary and we search. We choose we pick the largest and the smallest. The largest must be the absolute maximum. The smallest the absolute minimum. So, for instance, if the boundary is given by, let's say, the unit circle, so set of all x, y, x squared. Not the unit circle. The boundary is given by the unit circle. The domain which we consider is the closed disk of radius 1. So what we have to do is in order to find the absolute extrema, which we know which must exist because of the extreme value theorem, what we have to do is, okay, we have to check inside the domain at all critical points, and we have to check at the boundary. Okay. The first step is always to find the critical points, which is, for this example, is very easy because the derivative with respect to x is just 2x. The derivative with respect to y is 4y. So we see from this there is only 1 point, 0, 0. Okay, and the function value is the only critical point. This point is also inside our domain, so we have to consider it. The function value at this point equals to 0. Of course, we see already from the function it must be the minimum, but this is just a very easy example to demonstrate how the method works. So this is kind of the first step. Then the second step is checking the boundary. So we have the function f of xy is equal to x squared plus 2y squared, and we have to check on the curve x squared plus y squared is equal to 1. But also in this, for this example, almost trivial because you can solve this here for y. You plug this in, so you get the function g of x, which is then 2 minus x squared. And you see, and the x, because of this condition here, so the x must be between 0 and 1. So the x is between 0 and 1. And you see that, okay, so we have, at the boundary, we have to search the maximum and the minimum, between -1 and and 1. Sorry. So we have to find on the boundary the largest value and the smallest value, but of course this is easy here for this function. So the largest value will be 2, the smallest value will be 1. So on the boundary, the minimum equals 1 and the maximum equals 2. So we have only reduced our problem of finding the absolute extrema just to 3 points, to a set of 3 points, 0, 1, and 2. And the largest one of these 2 is the absolute maximum, 0 is the absolute minimum. Okay. So that's how the method works. Okay. So you have given a function on a closed and bounded domain. Okay. We know that such a function must attain absolute maximum and absolute minimum. What we do is we check the function value at the critical points inside the domain, and we check at the whole boundary. Okay. Of course, here for this trivial example, you could use some easy inequalities or stuff like this in order to solve this example. Okay. So here it's not very complicated. You don't necessarily have to use this method, but it's easy to demonstrate the method. And you see that if the domain is much more complicated, like maybe let's keep this. So if the domain is very complicated, okay, then checking at the critical points inside normally is not a problem. But then you still have to solve a problem of the type extreme value problem of the type. You have given a function, and you have given another function which describes the boundary. Okay, and you are asked to find the maximum and the minimum of this function given the boundary under this constraint. Okay, so for this example, it was easy. Why was it easy for this example? Because we could solve this equation for y and we plugged in y. Okay, but if this g of xy is very complicated, maybe it can, because this is a little bit like implicit differentiation. Okay, implicit differentiation. We also want to find the derivative of y as a function of x. Okay, of something like this here. And we always use implicit differentiation if we cannot solve. Okay, but actually before we use the method, we have to show that it's possible to solve. Okay, that this problem makes sense. Now, here for this general type of problem, okay, you are quite often in a situation that actually you have the boundary given like this here. It would be possible to solve for y, but you cannot do it. Okay, then you would like to have a method like implicit differentiation. So you do not solve here first for y and then plug in. Okay, and the final method which we are going to discuss is for this problem. So given a function of 2 variables and given a curve, we want to find a method which allows us to find the absolute maximum and absolute minimum of f on the curve. Okay. Some problems of this type are easy because like here you can sometimes solve for y. You just plug in and you reduce it to a problem of a function of 1 variable. So sometimes very easy, but the method, the power of the method is revealed whenever this is not solvable for y, and the method still applies. And this is the so-called method of Lagrange multipliers. We will see another advantage of the method is even so if you can solve for y, the method is easier to use than first solving for y and then solving a problem for a function of 1 variable. Everything is a little bit in similar flavor to the method of implicit differentiation. I mean, the advantages of this method are exactly the same. Now, okay, so the problem is you've given a function and a curve. Okay, so find absolute extreme values. So this is some curve, absolute extreme values. of f on C. Okay, and we wanna what we wanna have is a systematic method. In order to do this, of course, once more, to stress this once more, okay, if you can solve here for y or for x, you can just reduce the problem to a problem for a function of one variable. This you can solve easily, because normally here also if you can solve for y, then for x you will get some range, okay, and then you just use the closed interval method in many cases to solve this problem. So what is more important for us is the situation where we cannot solve for y, or where we either can solve for y, but the resulting problem is getting much more complicated. Okay, now let's maybe before I explain how to solve this problem or how the general method works of Lagrange multiplier, let's maybe look at some examples, whether we can see something, some conditions which are satisfied by an absolute extrema which solves this problem. Okay, so this is once more the disk which comes with the textbook. So you see we are talking now about Lagrange multipliers. And here you have this kind of very nice animation. Okay, so what do you see here? You see the following. This here, the gray surface, okay, is the graph of our function f. Okay, so this is the gray one. Okay, then the blue one is this curve here, C. Okay, and here what you see is for every, because this curve one is this curve is in the plane. Okay, and what you see here are the corresponding function values, so the lifting up to the surface. Okay, now the red plane you see here are the cross sections, or which are parallel to the xy plane. So they will slice out some part of the surface, which we call level curves. Okay. So what you see in the animation is the red plane is going up and down. Okay. So this corresponds to different level curves. Okay, having a constant set value. Okay. And you will see this drawn here on the left-hand side. Okay. And as I have already explained, the blue one is just this curve here. Okay, so maybe let's start this. Now you see it. So here, because the level curve, so the plane is going up, so the level curve you see here has larger and larger set values. Now, okay, so if you look at the right-hand side, okay, you can easily see where is the maximum. Where is the solution to this problem here? You see, one solution is over there. I'm not tall enough. You see, over there. Right? And the other one, this is the absolute maximum is over there, and the absolute minimum is here, right? Okay, now we are close to the absolute. So here the absolute minimum, and roughly here the absolute maximum. Okay, so once more. Now, okay, so now we reach the absolute maximum value. Now we reach the absolute minimum value. Okay, what do you observe? What do you see if you look at the left-hand side? Once more, okay, so now we have the absolute minimum. Now we have the absolute maximum. What do you observe if you look at the left-hand side? once more, that everyone can see it. Now. You see what, if we plot the level curves here, okay, you see that it seems that at the point of the solution of this problem, okay, the level curves are tangential to the blue curve. Okay, because you see now is the solution. And now you see now is the solution, and exactly there the level curves and the and this curve here are tangential. Okay, this is the main observation. This already explains how the method works. But we have to find first an explanation why at the point of solution. So if I have a solution to this problem, and you plot for this solution the corresponding level curves of f, the corresponding level curve, then you will see that this level curve is tangential to this curve here. This is the main observation. Okay, so maybe let's plot another example. I plot another example. This is the example more or less from the textbook. So assume that the level curves of the function are given like this here. So we have here 7, we have here 8, we have here 9, we have here 10. So what I write here, the number I write here is the level, is the corresponding set value. So here everywhere the function f has the same set value, which is 7. Here the function has the same set value, which is 8, and so on. So these are the level curves of f. And I also plot so let's say this is our curve C. Now, what we have observed from this example is the following. This point here should be a solution to this problem. Okay, so this is what we have observed. So once more, if you have a solution to this problem and you plot the corresponding level curve, which is this one, this is the one we saw moving, okay, then the level curve at the solution should be tangential to the curve C. Okay. Now, what is the explanation for this? So I can also put it different. So the level curves are tangential, or put it differently, the gradient here at this point of G. Okay, so the gradient of G points in this direction. But the gradient of f also points in this direction, okay? Because the gradient of f, we know that the gradient, one of the properties of the gradient at this point of f is tangential. The gradient is tangential to the level curves, okay? So this is also the gradient of f. So we see that the condition must be at a point at the solution. So at the solution, x0, y0, we have, actually this is our guess, we have that the gradient of f at x0, y0, because the gradient is tangential to the level curves, but also the gradient of g is tangential to this curve at this point. Okay, so they must be parallel. So there must be a lambda such that we have this relation here. Okay, so we have that there exists a lambda that this holds here. Now, what is the explanation of this? Maybe you can see it already. It's not so complicated to explain, because you see, if you're at this point here, okay, then at this point the gradient of f and the gradient of g are the same. But we know that the gradient of f points in the direction of largest increase. Okay, so if you are standing here, okay, because your objective, what is your objective? You are standing on the curve, you look at the function value, okay, so for every curve, for every point here, the curve, a function value of f is attached. and you walk till you find the largest or the smallest. Okay, because you want to walk on this curve here, you look at the corresponding function value and you stop if you find the largest or smallest. Now, assume you reach this point here. Okay. Now, you know, if you look at the gradient, you know in which direction to walk such that the function is getting larger, namely here. Okay. Which means if you walk here or you walk here, the function value of f should get smaller. Okay, so here at this point, you should have an absolute maximum if you have this here. Or in the other direction, then absolute minimum. Okay, and sorry, here you have, because this is the largest, so this should get smaller and this should get smaller. But if this is not the case, okay, then you should be able to improve your function value. If you stand at the point where the gradient of f is not tangential to the curve, okay, then you should be able to make the function value of f larger by walking on. Okay, so this is not a surprise that you get this condition here. Okay, of course this is not a proof. Okay, I just described why this is true. Now, of course, it's also possible and not complicated to give a proof. Because the same method holds for functions of 3 variables. So you have given here a function of 3 variables, and you have given a surface, and you want to solve the same problem. And functions of 3 variables we cannot depict easily. Of course, we could depict the level surfaces, but this would give a 3-dimensional picture from which you might not see anything. Okay, so let's prove this, what I just explained heuristically by looking at functions of 3 variables. You will see the proof is not complicated. And now we have a level surface, not a level curve. Okay, so assume that f achieves an extreme value at let's say the points x0, y0, z0. Because I have a level surface, so first I also assume that I have a parametrization of this curve C. Okay, so this is some level surface, and I assume a parametrization of C is given by let's say some vector function r of t. And let's say that let's assume that r of t0 is our point x0, y0, z0. Now, if I look at the function this one. So if I look at the function f of x of t, y of t, z of t. So this is like if you consider the case of 2 variables. Okay, this is the blue curve you saw here on the right-hand side on the surface, lifted to the surface. Okay, so this is this one. So what we want to do is we want to find the absolute maximum and absolute minimum of this function f. But this is now easy. This is a function because this is a function of 1 variable. Okay, so we know that because I assume that at t0, okay, I assume that this function here has an absolute extrema, so we know that the first derivative at t0 must be equal to 0. Okay, so you know that the first derivative at t is equal to t0 is equal to 0. This is Fermat's theorem, because we know that there is a function of one variable. We have an extrema at t0, so the derivative must be equal to 0. But this derivative here you can compute by the chain rule. So you see that if you compute this derivative, you have the partial derivative of f with respect to x times, and then you have dx over dt plus the partial derivative of f with respect to y, and then you have dy over dt plus the partial derivative of f with respect to z, and then you have dz over dt equal to 0. Okay, but this here means, of course, everything is evaluated at t0. Okay, this means that the gradient of f times the derivative of r at 0 is equal to 0. Okay, and but this already shows that this curve here must be tangential to the level curves. Okay, because the gradient of f we know is tangential to the level curve of f at the height, at the point x0, y0, z0. I should say at z0. Okay, the level curve with the value z0. Okay, we know that the gradient is orthogonal to this level curve, but this shows us that the level curve and this not curve, surface, always surface, so that the level surface and this surface here must be tangential, which in turn means because we know that the gradient of g, okay, is also because the gradient of g at this point here gives a normal vector to the tangent plane at this point here. Okay, so if the gradient of g, and this is an assumption we need, the gradient of g should be not equal to 0. Okay, because otherwise it is not. Because otherwise it gives a useless information. Okay, because the 0 vector is perpendicular to every vector, also parallel to every vector. So unless the gradient of g is not equal to 0, okay, we get that the gradient of f must be parallel to the gradient of g. And this is what we observed in the animation I showed you for functions of two variables. So in order to summarize, we have the following method. Or any questions to this? Okay, so the method of Lagrange multipliers works as follows. So first, because we know that, so we have given a function of three variables, f, and we have given a surface, g of x, y, z is equal to k. So the first thing we have to do is we have to solve this here. And we have another condition, which of course is g, x, y, z is equal to k. Okay, so find the solution of this system of equation. Okay, find all solutions. Then the second step is evaluate them. Evaluate f at the solutions, pick the largest and the smallest. The largest is the absolute maximum, the smallest the absolute minimum. So evaluate f at all solutions and pick the largest and smallest. Okay, and you have to notice, because this here, because we are talking now about the case function of 3 variables. So this here, actually, because this is a vector with 3 coordinates, okay, so this gives you 3 equations, and here you have a 4th one, and you have 4 unknowns, x, y, z, and lambda. Okay, the lambda is called Lagrange multiplier. That's why the method is called method of Lagrange multipliers. Okay, and the similar method for functions of 2 variables. Now maybe let's look at an example. Let's maybe go back to the example I discussed before, just to see how this method works for the for this example. We had to solve here this problem. Okay, so actually we were looking at this function on the disk with radius 1. Okay, and because of our method, in order to find absolute maximum values, we first looked at the critical points inside the disk, and then we looked at the boundary. And this corresponds to the second case here. So and this kind of problem, of course, can be much more easily solved by first solving for y. But let's just check how easy or how complicated is the method of Lagrange multipliers. So you have 2 equations. Okay, you have this equation and this one. Okay, so the first equation. Sorry, this is x squared. Reads as follows. So you have 2x is equal to lambda times 2x. And then you have 4y is equal to, and you have lambda times 2y. And then you have the last one, x squared plus y squared is equal to 1. Okay, but this is not complicated, because you see for the first one, okay, so you have x times 1 minus lambda is equal to 0. Okay, so you have here you get here 2 solutions. X is equal to 0. Lambda is equal to 1. Okay, if you have x is equal to 0, then from this equation you get y is equal to plus minus 1. Okay, if lambda is equal to 0, then you if lambda is equal to 1, sorry, then you see that if we look, of course, for this equation, wait a moment. For this equation, then becomes y is equal to 0. Okay, so if lambda is equal to 0, if is equal to 1, sorry, we plug this in here, then this becomes here y is equal to 0, and then we plug this in here, and we get x is equal to plus minus 1. Okay, so we have to check 4 points. Okay, so if we plot the picture, then you see that we have to check here x is equal to 0, so those 2 points, and we have to check those 2 points. Okay, and you easily see that the function value, if x is equal to 0, and you have this here as 2, and if y is equal to 0, and you have this here as 1. Okay. So here and here the function value is 1, and here the function value is 2. So the maximum is 2, the minimum is 1. Of course, for this easy example, you do not need the method of Lagrange multipliers to solve it. Okay, but you see how this works. Okay, so any questions to this? For instance, last time we looked at the example, we had a box made of cardboard. We had, I think, 12 square meter of cardboard available, and we had to find the box with the largest volume. Okay, so this means because the volume of such a box is x times y times z, and the surface area is 2xy plus 2yz plus 2xz is equal to 12, we have given this problem here. Okay, so once more, you have 12 square meter of cardboard. You want to make a box, okay, which has maximal volume. Okay. Now, of course, this problem also not too complicated, because you can say, okay, this is not complicated because I solved this here for instance, Z. You plug this in, and then you use just the usual method by you take partial derivatives with respect to x. Then partial derivative with respect to y, and you solve the corresponding system of equations. We have done this last time, okay? The only unpleasant thing is that if you solve this for z and you plug this in, the function you get is quite complicated, not very complicated. But for such a function, computing the derivative, you might make some tiny mistakes. But if you look at this setting, it looks much more easy. And the method of Lagrange multiplier avoids that you have to solve first for z. Okay, so here this is a good example which demonstrates that Lagrange multipliers are easier to use here. So actually we can erase here the 2. Now we have two equations. Okay, so the first equation is if we use Lagrange multipliers, we have to compute the gradient of f, which is equal to the gradient should be equal to the gradient of g, where this is here g, and you have this condition here. Okay, so you have this system of equations. Now, here you have three equations. Okay, so first you have the partial derivative with respect to x, which is yz is equal to lambda times, and here we have to compute the partial derivative also with respect to x here of this function. So what we get is y plus z. And actually, all the others are the same because of symmetry. So you have here x, z is equal to, and then you have lambda x plus z, and then you have xy, which is equal to lambda, and then you have x plus y, and then you have xy plus yz plus xz is equal to 6. Now, you see that the unpleasant thing using the method of Lagrange multipliers is you are ending up with something like this here. Okay, it's not a system of linear equations. This system of equation can be quite tricky. Okay, and you might say, okay, maybe it's still better to first solve for z and then take the derivatives. But here, this system is not too complicated to solve. Okay, but normally you need some ideas to solve this such a system of equation. There's no general method. Okay. But you observe here that because you have here this nice symmetry, okay. So an idea you might have is to make it even more symmetric, or I should say to make the left-hand side the same. So you multiply the first equation with x, the second equation with y, the last equation with z. Okay. Here you have to be careful because you add solutions because x could be equal to 0. Or y could be equal to 0, z could be equal to 0. But this is not a problem for us because we want to maximize v. And if x is equal to 0, you certainly do not get here the maximum. Okay, so you do not lose anything. So you have to be careful if you do something like this here. But then you see that once you do this, once you do this, you can equate the first and the second. So from the first and the second, equating them, what you get is lambda x y plus xz is equal to, and then you have lambda xy plus zy. And equating those two here, what you get is lambda xy plus yz is equal to lambda xz plus yz. Okay, now if you look at the first one, okay, you have to consider two cases. First case, lambda is equal to 0, obviously a solution. Okay, so if you look at the first equation, case 1, lambda is equal to 0. But if lambda is equal to 0, those are all 0. Okay, so at least 2 of x, y, and z must be equal to 0. Okay, but this again obviously doesn't give you the maximum. Okay, then at least 2 of x, y, z are 0. Okay, but this doesn't give you the maximum. So you can assume case 2, lambda is not equal to 0. If lambda is not equal to 0, you can erase it from here and from here. And then you see that what you get from the first equation is x is equal to y. Right? So if you can erase lambda, then you can erase this one. And then you have this equation. But we already observed that z is not equal to 0. So x must be equal to y. And from this equation, you see you can erase this one. Then you can erase this one. And then you have xy is equal to xz. But we have observed that x is not equal to 0. So y is equal to z. So all three must be the same. And this means the solution is given by a cube. This we have observed also on Monday. You see here that sometimes the problem by using Lagrange multipliers, okay, is that the resulting system of equation sometimes complicated. Okay, but here it's not too bad. Okay, some tricks and you can solve it. But I should also stress you have to be very careful. Okay, if you multiply with something like this here, you have to take new solutions into account. Okay, so you have to be careful here when solving them, because if you multiply with 0, then this gets trivially true and you get solutions. Okay. You also see that when we saw this for the first time, these 4 equations looks complicated, but it didn't turn out to be that complicated. And you see, you will maybe agree that this is easier than plugging in, first solving this for z, then plugging in and then taking derivatives. Okay, because when you take derivatives here, you might easily make a mistake. Normally, so this holds as we know for all n. The case n is equal to 2 is easy to prove. Then general case n by induction. It's also not complicated, not so easy, but also not complicated. But another very easy method is using Lagrange multipliers. Okay. Now the question is, okay, it might not be very obvious. Okay, how do you want to prove this by Lagrange multipliers? You have to choose a function f. Which you have to maximize, and you have to give a constraint. Okay. Now the function f is because we want to maximize this here. We want to prove that this is the maximum. So what we look at is the following problem: f of x, y, f of x1 up to xn. I should say the method of Lagrange multiplier also extends to function of n variables. Okay, the same method, because here we have a function of n variable. So here the nth root, this is something we want to maximize. And what is, maybe the constraint is a little bit more tricky. So what we choose is this one. Xn is equal to a constant, where c is a constant. Okay, where c a constant. Okay, now, maybe it's even better to replace this function here. So let's look at this function where we have here to the n's. Okay, so and we maximize this function here, okay, instead of this one. Okay, so maybe call this a new function f bar x1 up to xn. Okay, so the method of Lagrange multipliers tells us, okay, we have to solve, we have to find the solutions, all solutions of this system. So this here should be g of x1 up to xn of this system here of equations, and you have this one x1 plus and so on plus xn is equal to c. Okay, so let's write out this system. So here we take the partial derivative first with respect to x1, what we get is x2 up to xn is equal to, and here the partial derivative of the function g with respect to x1 is just 1. So what we get is lambda. Okay, and then for the next one, okay, if we take the partial derivative here with respect to x2, the x2, we have to remove the x2, or others are still there. And this is again equal to, here we always get 1. Okay, so you see that the system of equation, the last one is with respect to xn, so here the product is up to xn minus 1, the last one is removed, is equal to lambda. Okay, and we have this one. Okay, now here you can use, because the reason why I chose this example is very similar to the previous example, okay? Because you see that, again, the trick is you make all the left-hand sides equal. So you multiply this here with x1, and you go on, and you multiply this here with xn, then all the left-hand sides are equal. Okay, this is the trick. You have to be careful, x1 could be equal to 0, but this doesn't matter for us because we are interested in finding the maximum because we want to find the upper bound. Okay, so it's not important for us if x1 is equal to 0. You have to be careful here. Now, this will give you new equations. Okay, so from this one you will get new equations which are if the first and two will give you lambda x1 is equal to lambda x2. Okay, and you go up like this. The last one, and this one gives you lambda x1 is equal to lambda xn. Okay. Now you see two cases. Lambda is equal to 0. This is a solution of all the of this here. Okay, so lambda is equal to 0. But if lambda is equal to 0, at least one of them is equal to 0. So this is equal to 0, and we get the minimum, not the maximum. If we do not look at negative values, I should say. Okay, but we are interested in finding this upper bound. Okay, so the case one is lambda is equal to 0. It's not interesting for us. Okay, not interesting. Now the second case is lambda is not equal to 0, but then you get x1 is equal to xn. Okay, if lambda is not equal to 0, all of them must be equal. And but if you plug this in, because we have one more equation, this one. If you plug this in into this one, then you get that xi is equal to c over n. Okay, and this is the maximum. Okay, so you see that if I remove this here. Of course, actually, we have here another, because we want to find, we have to assume that all of them are positive, okay, or non-negative. We have to assume this as well, okay. But this doesn't matter because this here is an extreme. Here is an extreme value of this function, even if you have negative values. But we are just interested in the case where x1 up to xn are all positive. But this is anyway. This is positive. So the maximum of this function is achieved when all of them are positive. Now you see that from this we get that x1 up to xn is equal to is smaller equal to. Wait a moment. Something is. So also the nth root, of course, is maximized. This value. Wait. Something's wrong. I haven't computed actually the maximum. Sorry. You see that. And for this choice, okay, the maximum is given by c to the n over n to the n. Okay, so you see that the nth root of x1 up to xn is smaller equal than. So this is the maximum, the nth root of this. If I take the nth root, so c over n, but c was this here. So x1. That's it. That's the proof. you see, this is kind of, if you have seen other proofs, this you will maybe agree, this is more easier. Okay, because I do not have to do a lot. And similar, you can use, in our textbook, you can find a similar example. You can use the method of Lagrange multipliers to also prove the Cauchy-Schwarz inequality and so on. Okay, so any questions to this? Maybe you have seen this method in physics, because in statistical mechanics there is something where they discuss the entropy. They are normally interested in maximizing it, and I guess you have learned. I don't know whether you have learned this in physics, but because this leads to a constant which is called the Boltzmann constant, and in order to find to maximize the entropy under some conditions, you also use this method of Lagrange multipliers. I guess maybe you have seen it in physics. Anyway, if you haven't seen it, there will be an example in the next assignments where we will discuss this kind of situation. And it's also using the method of Lagrange multipliers. So maybe you have encountered this method already in physics. I'm not sure. If you have a function of 3 variables, okay, you can actually also give 2 constants. So we have the following problem. Okay, maximize, find the extreme values of f of z is equal to f of x, y, z under the 2 constraints now. Instead of only one surface, you have two surfaces. Okay, so those 2 surfaces will have an intersection. Okay, the intersection will be a space curve. So you have here those 2 surfaces give you some space curve, and you are interested in finding the extreme values of f on the space curve. Okay, and again, of course, it might be possible to take these 2 equations, okay, and remove 2 variables, and then or to you take this. This might be possible that you take these 2 and you remove 1 variable and you solve the remaining one for some of the variables and plug this in, and then you would get a problem for a function of 2 variables, and they could use our usual method. So sometimes it would be possible to it might be possible to reduce the problem, but we wanna again discuss this problem if we are not able to reduce the complexity, the dimension of this problem. Now, here you have a similar method. Namely, you have to observe. Okay, you have those 2 surfaces. Okay, they meet in a space curve. Okay. Now, what we know is that the gradient. Okay, is if you have a maximum. Okay, you assume you have an extreme value. Okay, at some point. Okay, then what you know is that the gradient of G1, this you know anyway, is orthogonal, okay, to the tangent plane at the point where the maximum occurs, and the gradient of G2 is orthogonal also to this tangent plane here. Okay, so but this means that the gradients are orthogonal to the curve of intersection. So the gradient of G1 and the gradient of G2 are both orthogonal to the curve of intersection. Okay, so observe that. gradient of G1 and the gradient of G2 are orthogonal to the curve of intersection So you see, if you have two surfaces, okay, and you should compute at some point the tangent. This was like today the in-class homework. Okay, so if you have two surfaces and you should compute at some point the tangent of the curve of intersection, okay, you observe that the gradients are both orthogonal to the perpendicular to the tangent. Okay, this is very easy because the tangent at some point. Okay, the tangent must be contained in the tangent plane of this surface and in the tangent plane of this surface. But the gradients are normal vectors to the tangent planes. So if you have to compute the tangent of the curve of intersection, okay, what you have to compute is a direction which points in direction of the tangent is the cross product of those two here. This is what you had to compute today in the in-class homework. Okay, and now if you use the same reasoning which you have seen before for the method of Lagrange multipliers, then you will observe that also this is because of Fermat's theorem. Also, the gradient of f is orthogonal to the curve of intersection. Okay. Because what you do is, okay, you parameterize the curve of intersection, you plug this in here, you use Fermat's theorem, you see that the gradient must be orthogonal to the tangent line. Okay, so you have three vectors, this one, and the gradient of f, which are all orthogonal to the curve of intersection, or I should say to the tangent line. Okay, at a point where an extreme value occurs. Okay, so this vector, and the gradient of f must be in one plane. They must be coplanar. Okay, so the gradient of f is also orthogonal to the curve of intersection Okay, so the gradient of f, the gradient of G1, and the gradient of G2 are coplanar. Okay, which means that the gradient of f is equal to must be in the plane spanned by those two vectors. So you have some lambda and some mu, such that you have this equation here. So here, for two constraints, the equation which you have to solve is this one. Okay, so you have two Lagrange multipliers, lambda and mu. This gives you here three equations because you have five variables, x, y, z, lambda, mu. So you need two additional ones, and here you have two additional ones. So you have overall, again, a system of equations. You have five equations. You solve it for the five unknowns, x, y, z, lambda, and mu. And for all solutions you evaluate f, you pick the largest, and you pick the smallest, and that's it. Okay? You see that this method of Lagrange multipliers adds here. The original problem has just three independent variables, okay, but we are adding two here for this case, okay. So we actually this kind of seems like we make the problem harder, okay, but overall it gets easier. It gets easier to solve. An example which appeared in a previous Heukhau. So given the curve, let C be the curve intersection of x squared plus y squared is equal to 4. But we are in the space now, so this is a cylinder, and a plane x plus y plus 2z is equal to 6. Okay, find the maximal set value. Find the maximal set value of C, or on C. Okay, so here our function f of x, y, z is equal to z, because we have to maximize the set value. Now, so the method of Lagrange multipliers works as follows. You look at the gradient of f is equal to lambda times the gradient of g1, which is this one, plus mu times the gradient of g2. Okay, so this gives you a set of equations. So the first one is 0 is equal to, with respect to x, so we have 2 lambda x plus, and here also with respect to x, which gives 1, so mu. Then we have 0 is equal to, this is the second one, so here we have 2 lambda y plus, and here we have again, so it's the same equation. Now, for the last one with respect to z, so we get here 1. Here with respect to z, but z is not there, so it's 0. And here we have 2, so we have 2 mu. These are 3 equations, and we have this one, x squared plus y squared is equal to 4. And we have x plus y plus 2z is equal to 6. Now, you see, of course, there are different ways to solve something like this. But you could first solve for mu, you plug this in here, and then you express lambda. But it's much better to subtract those two. Because if you subtract those two, what do you get? You get lambda x minus y is equal to 0. Okay, so this will give you 2 cases. So case 1, lambda is equal to 0. Okay, but if lambda is equal to 0, this will imply that mu is equal to 0, but this violates this here. Okay, so this is not possible. Okay, so case 2, x is equal to y. Okay, and for this case, you choose this one. So what you have is 2x squared is equal to 4. So x is equal to plus minus square root of 2, which means y is equal to plus minus square root of 2. And then you use this in order to compute this here. Okay, so z is equal to 3 minus, so they are the same, so plus minus. If you have here plus, then what you get here is minus square root of 2, and you have plus. Okay, so the solution is given by (3 plus square root of 2). You see that maybe once more a few words to this system of equations. For such a system of equation, there are always, in many cases, actually not solvable. Okay, because I think there is, if you go to one of our restaurants, the one which is next opposite to the Kirchhoff Iguan, to the Department of Applied Mathematics, if you walk in and there is a board on, if you just walk in, there is a board on the left hand side, and you will see there is an example posted there. This example looks like you can use the method of Lagrange multipliers, because it's exactly the same problem. You have some function, maximize it under some condition. But this example more tricky because you can theoretically you can do it, but you cannot solve this system of equations, so it's useless. Actually, there are quite a lot of such examples which are solvable with some trick, but if you use the method of Lagrange multipliers, would be either get much more complicated or not really possible. Okay, the reason this system of equation is getting much too complicated. That's why such examples maximize something under some constraints also appear quite frequently, or used to appear quite frequently in Math Olympics, because sometimes many examples you can find easier methods. You use some of the standard inequalities or something like this. You should not do this for the, even if you find such a way, you should not do this for the assignment. I mean, you can also write down if you find a better way to, a more easier way, without using our tools to maximize it, but for the assignments you should use the methods just to see how this method works, because if I choose two easy examples, then very often it's possible to completely avoid this method and just rely on some standard inequalities to solve it. Now you see the crucial thing here, the thing which is which sometimes makes the method, of course you can theoretically you can apply it, but you cannot really carry it out, is you have to solve a quite complicated system of equations which is in most of the cases non-linear, not a linear system of equations. This is not complicated here, but even so it's solvable, there are always different ways to solve it. It would look quite natural first to solve for mu, then to plug this in here, and then solve, for instance, the first one for x, the second one for y, but then everything depends on lambda. You plug this in here, you get lambda. Okay, this would be one but much more complicated than the one which I used here. You see, this is much easier if you subtract those two. You understand what I mean? We could solve this for mu, then we can plug in here mu, then mu is a constant, then we can express x and y here, but as a function of lambda, we plug this in here, we compute lambda. Would be another way, but much more complicated than this one. So here, once you encounter this system, it pays off to think a little bit, to try to find the easy way to solve it. Okay, like this here. Okay, so of course, sometimes most of the cases not possible. Okay, but sometimes possible. Okay, you saw in artificial examples possible, but you also saw that for the proving the geometric arithmetic inequality also possible if I just use the right trick to solve this system of equations, which is not such an artificial example. So the step which is more complicated is this one, but the rest is rather routine, and the method is easy to apply, and is a general method to solve such problems, which always works, because if you cannot solve something like this exactly, you can use a computer algebra system, and for instance, Maple can also solve non-linear system of equations, or at least approximate the solution. There are very powerful numerical methods to do this. So this is a general method which always works, whereas if you rely on some inequalities, of course this might work, but this is a kind of trick, and for every example you have to find a different way to solve it. So this is the difference to, of course, some of those examples, even in high school, you could solve them by using some inequalities, and that's why in the Math Olympics such examples show up, because many of them can be solved by some tricks. But the difference is that this is a systematic method which can always be applied, whereas relying on some inequalities, you might have to choose a different inequality all the time for every example. So you have to find a solution which is specific for the example. But this is a general method here, which you see, which you can apply whenever you, or try to apply whenever you have a general problem, like you have a function, you have to maximize it on a curve, or minimize it on a curve. Okay. Any questions? So this concludes chapter 14, and next time I will start to teach chapter 15, which is then the final chapter we have to cover. Please help me to identify your name and